Okay, let's get started. So based on the hecticness of the end of the semester, I am going to suspend the quizzes. So we won't have a quiz on Monday. I will still post questions to ponder today because I think those are helpful for the exam. But I mean, the quizzes. The purpose of the quizzes was to make sure people come to class and look at the lectures and based on exam performance and things like that. I'm pretty sure you guys are actually doing that. So why add an extra thing in the mix when everyone is running around with trying to get senior design wrapped up and get the exams going? So, so that's it. I still have exam. If you didn't get your exam on Wednesday, or I still have some exam ones that people never picked up, grab them after class. Okay, so I'm sort of surprised that, well, not surprised, but I'm I guess pleased. I was worried that we were sort of really off schedule at the end here, but I think it worked out well that we spent so much time on sort of basics at the beginning and in steel, because as you'll see as we go through the titanium alloys, there's nothing really new here, right? All as it is a different material system, and the only real wrinkle is now we have to think about hexagonal materials, hexagonal alpha, and the properties associated with HCP as we go through the alloys and applications. So I plan to do this today and Monday, and then I will be putting together. Unfortunately, I think I am still a little behind. Took a little longer in the steel than I had anticipated. So we will have one recorded lecture on nickel, just to make sure that we can finish all that up with enough time to review before the final exam. So in trade of no quizzes, I guess I'm going to ask you to watch one more lecture. So I hope that's not too much of a burden. Okay, so just as a reminder, we're going to classify our titanium alloys into a couple big broad categories of either alpha, alpha plus beta, or beta, with near alpha and near beta alloys sort of straddling the middle based on what fraction of beta stabilizers they have. And the important elements to remember, right, are what are the key alpha stabilizers and what are the key beta isomorphous stabilizers and what are the key beta eutectoid formers, right? And that the group 4 elements, zirconium and hafnium plus HCP tin, are going to be neutral with respect to the phase diagram, right? So if we start with alpha alloys, right, we can classify these as sort of 3 big groupings, right? We have our fully alpha alloys, right, which have either alpha stabilizers or neutral elements in them, right? So these are going to be fully HCP alloys. The near alpha alloys, which can contain up to 2% beta stabilizers. And then the class, which we haven't mentioned yet, really, which are the age hardenable alloys. And this comes across because of the titanium copper phase diagram that we get fine dispersion of secondary phase particles that behave very much like aluminum. So if we just think about the full alpha alloys, of course we have commercially pure titanium, titanium oxygen, right? So this is basically the oxygen content's going to do what? Right? Strengthen, right? So adding the oxygen to the titanium is strengthens, and then aluminum tin alloys, right? And depending on how we process them, we can get a range of microstructures, right? So if we go up above the beta transit and cool very quickly, we can get a martensitic phase, right? We can get a fully martensitic structure that we can then temper, right? We can have our Widmanstätten lath-like alphas or an equiax structure. How would we get an equiax alpha structure? Right. Where is, if we're coming down from the transits, where does the alpha nucleate?
The grain boundaries.
At the grain boundaries, right? And then we talked about how they're either going to coat the grain boundaries and then grow in like Widmanstätten plates, right? So how do we get an equiaxed?
Large quench.
Oh, I mean, think about the processing, right? How have we achieved a good, nice equiax structure in steels? What's that? So either low undercooling or thermomechanical processing. Recrystallization. What? So basically a full anneal, right? We're going to recrystallize and develop a nice equiax structure. What's the? Does anyone I guess the people in Mod Sim right now probably have seen this based on one of the exercises. What sort of texture do we get out of rolled and recrystallized HCP? Where's the C-axis? Throw out a guess. If it's wrong, it doesn't
45-degree angle.
Basal. Right? You get a basal texture, so you have the C-axis normal to the sheet, right? So you have, which is good because it gives you relatively a transversely isotropic properties in the sheet, right? So it doesn't matter if you cut out along the rolling direction or orthogonal or 45, right? Because those prism planes are randomly oriented, right? But if you were to do compression, say through thickness, right, you'd have a different response because you're pushing on the compressing on the C-axis. So depending on what you want, titanium alpha sheet can either be strongly isotropic or strongly anisotropic, right? So full alpha alloys, in terms of compared to other titaniums, not so great in strength. Why is that? One phase, right? Ductility, relatively good. Very poor formability, right? Because we don't have that. We don't have an easy mechanism for plasticity along the C-axis of the crystal, right? We have to invoke either C plus A pyramidal slip, which has long Berger's vectors, or twinning, right? To get, so we don't have very good formability, but we do have very good creep response because of that, for the same reasons. Right. If we move up to the alpha, the near alpha alloys, right, we're putting in small amounts of beta stabilizers, right? And if we look at the compositions that we threw out here, IMI 685 and 679, right? You can see we've got titanium aluminum and tin in 679. Zirconium's neutral, right? Molybdenum is a beta stabilizer, so we've got a mix of alpha and beta stabilizers, right? And then, so what are the zirconium and tin are neutral, aluminum's an alpha stabilizer, but these are there primarily for solid solution strengthening, right? Molybdenum's a beta stabilizer, and silicon does something interesting, right? It is going to form a solid solution in the alpha, and it's going to segregate to the dislocations, preferentially to the dislocations, which is going to give us impeded initial mobility, right, for yield. So this is sort of like a dynamic strain aging effect. Instead of interstitials, now we've got substitution. Right? So the increase in tin, the main difference between these two alloys, right, is the replacement of aluminum with an additional increase in the tin content, right? And the tin for high temperature applications happens to be a better solid solution strengthener, and it doesn't promote the A2, right? What was A2? We talked about it at the tail end.
Was it just hexagonal?
So it was hexagonal, but it was the ordered phase, right? The DO19 structure, right? So we would preferentially replace certain titanium lattice sites with aluminum, and that gives us basically a brittle, a more less ductile intermetallic, right? Because the ordering is preferential, right? So if we look at pure compared to pure alpha alloys, right, having a small amount of beta present, right, is going to mostly give us better formability, right? We've got more things that we can do by playing with the heat treatment, right? The compromise is the beta phase, having a little bit of beta phase in there gives you more options for creep, right? And so you have a little bit of loss of creep properties. And we can go through the basic alpha beta processing or beta processing steps, just that we talked about, right? Remember, alpha or beta processing is a hold above the transit, a hold in the two-phase region, and then a stabilization low in the two-phase region. Alpha beta process involves a rolling or a deformation step in the within the two-phase region. Right? And the other class is the age hardenable alloys. Right. So copper is a strong eutectoid beta stabilizer. Right. And basically, we go through a double heat treatment type step, right? So heating at 400 C, this is just exactly like similar rationale for what we did with aluminum. We have a heat treatment at 400 C, right, giving us a very fine dispersion of Ti2 copper, right, which is a metastable phase, very fine scale of precipitates, and then we do a secondary age at 475 to coarsen them slightly, right? And then that will give us a nice increase in strength, right? So this age hardenable titanium alloys behave exactly like the precipitation hardened aluminum systems, right? And the important alloy there is IMI 230, which is just titanium with 2.5% copper. Okay. I thought I had a picture of one in there. Okay, so that's those are the commercially important alpha alloys, and their main application is where we need weldability or creep strength. Right? The alpha plus beta alloys are the most important group, the most commercially relevant, and the key alloy there is, of course, Ti-6,4, right? 6 aluminum, 4 vanadium. Right? It's used, I have here mostly in forged components, but we'll see it's also can be cast. It's also an important powder metallurgy alloy, and now coming online, it's probably one of the most important additive manufacturing alloys. Right? It is, I think, the only titanium alloy that you can get powder for additive manufacturing. Right? I think if you look at what is actually being produced, it'll be 316 stainless is what a lot is being printed in, and then Ti-6. And just to remember, if we go through the beta processing, we get colony or basket weave microstructures. The alpha beta processing gives us the formation of globular equiaxed alpha. Right? And just sort of the difference in properties between those two routes. The tensile properties are pretty similar. Right? Doing the alpha plus beta processing, we get a little boost over the yield strength, a little boost in ductility because we've got these nice large regions of alpha that can deform to give us a little ductility. The yield strength comes from, we've got different phase compositions and different microstructures. So the within the transform beta grains, we're going to be quite a bit stronger. We lose fracture toughness. Where is this loss in fracture toughness from the alpha plus beta process coming from?
Your lath-like structure.
Yeah, right. We have we have more regions that we can propagate a crack through easily from these big globular alpha grains. We don't have to take as tortuous a path. So I've got slides here from, it's cut off, but these are from Jim Williams, who's a professor emeritus here, who literally wrote the book on titanium, right? If you just, the big, like 500-page titanium handbook, right? It's Ludwig and Williams, right? So Jim, he was at GE. He's former dean of the College of Engineering, member of the National Academy of Engineers. Right? So the titanium guy. But these are from a short course that he teaches every so often. But this is just sort of showing in a modern high bypass turbofan engine, like all the ones on large commercial planes. Remember, if you're not familiar with the nomenclature, it's high bypass because this big fan disc up here basically acts like a propeller, right? And most of the air going through the engine doesn't go through the actual turbine itself, right? It bypasses around the side, and it acts just like a propeller would, except it's enclosed in a shroud. So the fan discs, all this ducting, right? The compressor parts, the manifold out here, right? All of these are titanium parts. Where we won't see titanium is actually the hot section blades, right? That's the realm of nickel at the moment, but there's a lot of titanium in a modern aircraft engine. Right. So if we look at the fan disc, right, these dovetails are where the fan blades actually slot in to keep them mechanically secure. So this is Ti-17. I'll go through the composition of that in just a bit. But if we look at this, this is why there's a big push for additive to being able to construct these things, right? So if we start with this this part, the final part only weighs 370 pounds, right? But to get there, we have to start with a forging that's over a ton, right? So we start with 2,200 pounds of material, forge it, cut away the outer surface stuff, then machine this part out, right? So we're actually processing 6 pounds of high-grade material for every 1 pound that actually ends up in your component. And the rest of this has to go back through scrap and recycling, right? So this sort of highlights a major issue with titanium, and that's sort of the life cycle method, right? How do we take care of that? Part of it is putting in different manufacturing processes, right? So this is the spool. The compressor disc would sit on the outside of this, but these are made up of smaller sections that are then inertia welded together, right? So I would say, who here is familiar with inertia welding, right? Or welders, right? Basically, you have two cylinders. I'll throw a YouTube video up on Carmen. But basically, you take two tubes, put them together with some force, right, and then spin one, right? So you have a mix of initially some frictional heating, but then lots of heating that comes from the plastic work that's being done, right? And then as you compress forward, the softened material flows out, and then you have a solid state metallurgical bond, right? So the key thing with inertial welding is you're not actually melting, right? So you don't have a lot of the problems that comes with traditional fusion welding. So this is as Jim points out, a fantastic application of titanium, but it's a really expensive part to make, right? You've got precision machining, the welding, all the welding processes, and then further machining steps. But you can by doing processing routes like this, you drastically are able to reduce that buy to fly ratio, because now I don't have to machine this out of a solid billet. Right? Large fan blades are being produced as a combination of polyamide matrix composites with just titanium edges on them for wear and abrasion resistance, right? So, and then being able to cast hollow blades for weight reduction, right? So this is a big part of the efficiency of modern engines versus those previous ones, right? When you had only nickel blades, right? Now we can have very large structures while keeping the moment of inertia of all that rotating mass low. Right? Just showing this is just cast tie 6-4 with then hipped, right? Hot isostatic press to close up any casting porosity or casting defects that form, right? And so this sort of jumps into one of the reasons why tie 6-4 is so popular of a titanium alloy, right? It can be welded, right? It's a pain to do, right? I mean, you need a good welder. I can't do it. I blow through it every time. But someone skilled can do very high quality repairs on cast cast Ti-6-4 parts. So there's a mixture of the PMC, the polyamide composite, and titanium. Right. The big advantages over PMC are still lower weight. Right. Low flammability. Titanium can burn under hot enough conditions, or if you powder it. Right. But the big advantages of titanium are that it can be repaired, and just sort of the regime that we're interested in. So service temperature is up to about 600 C, right? Our alpha-beta titanium alloys are good for. Once we're above that, we start to move into the nickel region. And the reason for this is if we look at properties versus temperature, right? So this is specific yield strength, right? So this is yield strength normalized by density, right? And we can see that at low temperatures, we have quite an advantage for titanium, right? Titanium has our excellent strength to weight ratio, but our strength falls pretty precipitously at elevated temperatures. And if we look at Inconel 718, which is a very common nickel alloy that serves sort of the same. It's an older super alloy, but it's weldable, right? Right. And Haynes 242 is also. Yes. That's also weldable. Yeah. So those two alloys fit the same sort of spectrum, but you can see that they maintain their strength higher, longer into the higher temperature range before the drop off. Right. So in this case, it's not necessarily just a matter of what's the highest strength, right? It's what's going to maintain, right? We can have a lower specific strength material if it's going to maintain its properties for a longer range, right? And here at the bottom of the slide, they'll sort of put the relevant compositions for these alloys, right? Ti-17 is 5 aluminum, 2 tin, 2 zirconium, 4 molybdenum, 4 chrome, and if you add those all up, they give you 17% alloy composition. Right? So that's why it's called Ti-17. All right, and this is just sort of properties, right? So in recent years, 6242, this has been sort of pushed out a little bit into the 600 plus sort of range. But if we see, this is sort of the range that we're looking for. So we have yield strengths that are comparable to steels, right? With much lower density, right? Reasonable fracture and good service conditions or good temperature conditions, right? And I just sort of lead sort of 17 in there because that's sort of the high-tech alloy that's readily available commercially. Like there's newer alpha-beta alloys that push it, but they're very expensive and you can't really find them. Right? You can buy Ti-17 for applications. All right, fatigue crack behavior, they all behave basically the same. The interesting thing is creep behavior, right? So when in Professor Mills's class, did you guys talk about Larson Miller? I'm pretty sure the welders you guys talked about in welding metallurgy, right? So it's a way of characterizing, it's a design tool for creep. Basically, you take the time for a given stress value, the time to rupture plus some constant multiplied by the temperature. This is a constant for a given stress value, no matter over the range of temperature. So it allows you that for a given stress to relate the temperature that it's going to see to how long it's going to survive. Now, if you increase or lower the stress, right, you'll have a different C value here. This C is going to have a stress dependence on it, right? So you'll have a different Larson-Miller parameter. But it's a useful design tool for predicting the creep rupture life given the stress and the temperature that it's seeing, right? So if the Larson-Miller parameter drops pretty precipitously with temperature, or with, right, for a given, right? So basically, right, we have this big drop in Larson, big drop in Larson-Miller parameter with temperature, right? What does that imply? Right, that our rupture time has a big temperature dependence, right? Right. Whereas if we're right, if we have a narrow range, right, it's just a way of characterizing the creep behavior, right? So I forget where I was going to ask about this. I've got a question to ponder that I was going to throw out, but I'll just add it to the list. I forget. It's Friday. That's early. There's a sort of a design question, right? And so again, just some comparison of properties. I don't expect you guys to memorize these, right? These are really for reference, right? What is important is understanding the alpha-beta microstructure and how it connects broadly to the properties, right? So if we look at a slide like this, this is sort of a key type of things that points in the direction of potential exam questions, right? So here we've got two different microstructures, right, that came across from two different heat treatments. Here we heated above the transits and then cooled. Here we had another treatment that was 25 degrees below the transits, right? So we can see here we've got, it's a little hard to see on the thing. It's easier in the notes, right? We've got more of a basket weave structure here and more of a colony structure here. So what does that tell us about the cooling rates from the cooling from above the beta transits, which is faster, right? Faster cooling, slower cooling. The holding below, we see we have alpha, equiax alpha forming. We can see what about our prior beta grain size? It's probably a little hard to see, but we can outline a prior beta grain here, provided these are at the same magnification, right, versus a larger prior beta grains in here, right? So if we start, we've got balancing effects that we have to think about, right? Higher tensile ductility in this one. Why? we've got colonies that are well aligned. We've got nice regions of alpha, right? So we have a much less, right, we've got, if colonies are aligned with our slip direction, right, we've got nice long mean-free paths for dislocations, right? So we can think of a whole colony as being like a single alpha grain if it's aligned for slip. If it's not aligned for slip, then you have a strong Hall-Petch effect, right? But in the basket weave structure, we're always going to have, right? We always have these long grains that, even if they are well aligned for slip, are completely surrounded by other regions that are not, right? Toughness, right? Again, this is because we now have this tortuous crack path that we have to go through, right? Low cycle fatigue. Why is this going to be better in low cycle fatigue? Right? What's the primary difference between low cycle and high cycle? Right? It's going to be the amplitude of the stress, right? The amount of plastic deformation that happens on each cycle, right? And that's really the key, being easier to accommodate that plasticity on each cycle without causing damage, right? But then again, this is going to have a lower crack growth rate in the high cycle fatigue regime because you have that tortuous crack path. So if we think about low cycle fatigue, right? Small right? The main factors that are going to go into there are the beta recrystallization in the presence of continuous grain boundary alpha films. Right? The grain boundary alpha films give you sort of a nice short circuit path. Right? So large prior beta grains are bad for low cycle fatigue. The crystallized equiax small beta grains are going to be much better. Okay. A huge advance in the application of these alloys has actually been on the processing side, right? And how they're melted. And titanium processing, particularly this hearth melting, has been really a key area of processing development. So there's a couple melt defects that we have to be concerned about. So hard alpha, which is a nitrogen-rich region, I'll talk about that. Nitrogen-rich inclusion and high-density inclusions are things like tungsten that segregate together. And then beta fleck, we'll talk, this is composition caused by local composition fluctuations due to partitioning, which move your solvus, your transis up and down. And then that gives you, like if your eutectoid shifts up and down because of local composition fluctuations, it gives you very different microstructures. And we'll talk about that with the beta alloys. But it's pretty cool how titanium is actually processed now, right? And the key advance was this hearth melting technique. Basically, you've got a channel where the molten titanium flows. This is all done under vacuum, right? But you have, right, even if you didn't know anything about the process, how would you know that this is under vacuum? Well, besides that, the Ellingham diagram for titanium is pretty, right? You're going to know. But if you didn't know anything about what metal this was, right, how do we know it's under vacuum? Electron beam melting. It's hard to maintain a electron beam in air, right? But basically, you've got metal that comes in. You've got a series of electron beams that melt the metal, and it flows down to this pool where the surface is maintained molten, but through the depths it cools, and you have an ingot that's withdrawn from below. So you've got a directional solidification that's occurring, right? So it's a really awesome process. Very expensive, but pretty cool. Pretty cool process. So the defects, the critical defects in the melting are what is called hard alpha, right, which are nitrogen-rich sort of inclusions, and then high density inclusions where you get tungsten as an impurity, right, that can segregate, or other high density elements that can segregate. Right. And then this is we'll talk more about beta fleck with the beta alloys, but this just shows that you've got a gradient in microstructure that forms because of inhomogeneities, and they generally will, in the alpha plus beta alloys, will start at surfaces. You'll get composition fluctuations near the near the surface. Okay, so we're actually pretty good time-wise, right? Okay, so is anyone familiar with the issue of dwell fatigue in titanium? There was a couple plane crashes that had catastrophic rotor failures. I'll put up a case study on Carmen. What does anyone know what dwell fatigue is, or what a dwell fatigue test is? Right? So a fatigue test, you're just loading and unloading. Right? Dwell fatigue is you load to some value and you hold it for some time, and then you unload. Right? So you're dwelling at your high stress region. That high stress region is still below yield, right? But you're just holding it a little bit. And so this was a problem in the 80s and into the 90s that confounded basically everyone who worked on it until the invention of EBSD in the mid-90s. And then it became painfully obvious. Right? So we have two microstructures here, the same at the same magnification, right? And one of them will perform significantly better in dwell than the other. And the key thing is, can you tell any significant difference between these two from optical? I can't, right? You have a little bit of an over etch here compared to this one, right? But that's just metallography. That's just prep. That's nothing in the metal itself. And basically anything you run on this, X-ray diffraction to get macroscopic texture, chemistry, right? EDS or WDS to get composition fluctuations, you won't see anything, right? It wasn't until people were able to do EBSD that they saw things. So what is this big pink region here? Is it a single grain? What? No. No. What's the coloring on EBSD maps? Everyone in my mod sim right now should know this.
Grain orientation.
It's colored by grain orientation, right? It's the inverse pole figure coloring. So it tells you basically which crystallographic pole is going to be parallel with the sample direction. Right? In this case, we're looking at the sample direction that's orthogonal to the sheet. It's not a single grain. We see that it's not a single grain because this is the same magnification. These are the exact same samples, the same magnification. So we see this is hundreds and hundreds of grains that are all colored the same way. Right? So what does that say? Right? It means we have they're all grains that have the z-axis pointing the same way, right? So basically you have hundreds of grains that, from a mechanical point of view, what's the most important thing, right? What determines whether a grain is going to be plastically hard or plastically soft in titanium, in HCP, where the z-axis is pointing. So even though these are separated by potentially even high-angle grain boundaries, the rotation's about the z-axis. So this giant pink region and this giant blue region behaves like a giant single grain. Right? So this surprised the heck out of people when they saw it. Right? Why is this going to be bad for dwell fatigue? What's that? Propagation, right? So where in fatigue, if you're nucleating a crack internally, right? Most fatigue cracks will say start at the surface. But if you're nucleating a crack internally, where is it going to start? Inside your microstructure. Right? Just in a regular grain. Forget about these giant microtextured regions for a second. Where is a crack going to start? Right? Where are you going to have stress concentrations? On the grain boundaries, and it's going to be the grain boundaries where you have a plastically soft grain next to a plastically hard grain. One that's well oriented for slip next to one that's not, right? You're going to have, through cyclic loading, you're going to have a pile up of defects at that interface that's potentially going to lead to nucleation of damage, right? And then the crack has to propagate, right? But in a normal polycrystal, right, it's only going to propagate a short distance before it meets a different grain that has it, right? Now we got to deal with tortuosity of crack path. Here, all we need is a region that is well aligned for plasticity, large microtextured region, next to a region that isn't, to nucleate. Then when propagation occurs, it can propagate really readily across this entire region. And if we look at the scale here, this is 0.5 millimeter. So now we've got a easy crack propagation path on the order of millimeters in our sample. Right? Can anything survive under cyclic loading once you're in the long crack regime? Right? What's going to happen? Right? It's not going to work. So this microtexture, this macro zones, are a huge problem for dwell fatigue. Right? This is obviously going to be much better than this. Right? But with new forging processes, so this went back, and basically they said, we're not putting nearly enough cold work into this, right? So now it's forged for 4 or even 8 times larger strains, right? A lot of this is done in open die forging. So it's forged with giant hammer and anvil in one direction, rotate it 90 degrees, do it the other way, right? And instead of 2 passes like that, now it's 4 or even 8, right? But you get a much more complete breakdown, right? And from optical, right? If you go back to the optical images, it's impossible to tell, right? You see nice small grain size, right? If this is 100 microns here, right? You see grains that are 20 to 30 microns, right? Nice, clean, equiax structure, right? And so this just sort of shows the effect, the relative magnitude. This is regular fatigue, the red, right? Where you have those micro-textured regions versus random. Then in terms of dwell, you see the huge life debit, right? So the problem was people were doing regular fatigue tests thinking that we'll just go to a lot more cycles and not much is happening during the dwell region, right? There's not much happening that's time dependent because we're underneath our elastic, our limit, right? But as soon as you have those micro-textured regions, the whole thing came apart, right? And parts were failing with very small fractions of their expected service time, right? So where do we use the alpha plus beta alloys? Petroleum, right? Mining, sporting goods, armor application, not so much, but a significant potential in the future. Jewelry, right? I think right now tungsten and titanium wedding rings for men are insanely popular, right? Somehow titanium became a very masculine metal. Maybe potentially, I'm not as optimistic as Jim is on automotive use of titanium just because of cost, right? Cars don't like to put in, right? You can afford to put really expensive metals in an airplane, not so much in the family car. So unless cost comes down, I'm not so sure we'll see automotive applications. But like everything else in metals or material science in general, right? It takes 20 years to get a really awesome new material into an airplane or a car, but it will be in a golf club or tennis racket within a couple weeks because someone will pay for it, right? If it goes into a luxury product, the more exotic and more expensive, the better, right? So people were looking at metallic glass golf clubs. People were looking and buying them because you get, because of the elastic properties. There was for a while, I don't know if you can still get them, but someone was making beryllium golf clubs because of the incredible strength to weight, right? Not to mention the fact that if it ever got ground up, it could kill you, right? But people were doing it, and people were paying for it. So in terms of last slide, and then we're done. So in terms of alpha and alpha plus beta alloys, right? Lower specific strength, very competitive with steel, right? The lower the strength general, the more tolerant to processing variations we will. But the key thing is being able to play with the microstructure in beta versus alpha plus beta properties are going to is the main advantage in titanium. The huge range of microstructures and properties that we can get from fairly simple processing rounds, right? The microstructure again determines our average properties, right? Our extreme values, our fatigue and fracture, those are driven by very local microstructure, like local features, right? So it's not just the grain size that determines fatigue levels, right? And we have to be very careful with our melt-related defects. So Monday we'll do beta alloys and wrap up titanium, and then we'll have recorded lecture as an introduction to nickel over the break. Okay, have a good weekend.